So, hello everybody. I think we can begin. Welcome in this new webinar and thank you for joining us. I'm going to share my screen. Yes, here we are. So, I'm Suzanne Hernandez, Marketing Manager at NanoE. And today I will present you Zetamix filaments, technology and use cases. So this webinar is a back to basic. So I will explain you how our filament work, how produce a part thanks to our filaments, and what are the application of Zetamix technology. So first, I'm going to remind you a little thing about NanoE, our company. So NanoE is a company that has been created in 2008, and it's a company specialized in advanced material. It's an advanced material provider. We are specialized in ceramic powder for several industries, such as medical or semiconductors. So we are producing in ice square, for example, from 100 kilograms to 1 ton. But we also provide some custom-made products because we are really focused on innovation and we want our products fit the best to our clients' needs. So because of that, we are one R&D center with specialized engineer. So 2 years ago, we decided to make our powders, our ceramic powders, suitable with new shaping process, 3D printing. And that is why we decided to create Zetamix filaments. So our filament Zetamix, I'm going to explain you a little more about the technology and the advantages of these filaments. They are really affordable because this technology is suitable with any FFS 3D printers. Our filament can be used with FFS 3D printers, so it's quite affordable. It's also easy to produce, it's easy to print, because FFS 3D printers are one of the most easiest technology of 3D printing. For us, it's important to guarantee a good material properties for our filaments, whether it be ceramic or metal, because we are a raw material provider. So the final part you can have thanks to our filaments have good wear resistant, mechanical strength, and heat resistance, the same as our powder. Thanks to FFS 3D printing, it's allows us to print hollow out parts, internal channels, or in other intricate structures. The density of our parts is also something that is important for us, and the density is quite high, is 99% for our ceramic part and 95% for our metal part after the post-process. And last thing is one of the fastest 3D printing technology, because FFS 3D printing is one of the fastest. So now I'm going to enter more in detail about our offer. So we are a material provider. So we provide you the filaments in alumina, white zirconia, and black zirconia for filaments, and stainless steel and H13 for metal. We are not a machine manufacturer, but we provide this machine to make sure that our clients have all the right equipments to begin to print and produce parts. So we provide a printer, a Res 3D Pro 2, a debinding kit, and a sintering furnace, the Zeta Sinter. So what is in the filament? Our filaments are a mix between ceramic or metal powders and two kinds of binder. To make sure that our filament can be printable, we cannot make filament only with powder, and we need some binder to make it printable. So because of that, we have a post-process to reach the 99% density or the 95% density for metal. So I'm going to detail a little more the process. First, let's begin with ceramic process, alumina and zirconia. It's a 4 steps process with a file preparation and a printing, the same as with any FFS 3D printing process. And after these 2 steps, we have debinding steps, a chemically debinding process to remove a part of the binder. And after, we need to sinter the part under air to make sure that the part densify and reach the final density. For H13 filaments, the process is only on 3 steps process with the file preparation and the printing. But there is no chemically debinding steps. The sintering and the debinding can be operated in the same furnace and to be done under neutral gas and air argon. So it can be done thanks to our Zeta sinter furnace. For our stainless steel, it's a little different too. The file preparation and the printing remains the same, but the sintering has to be done under hydrogen, and this step cannot be done with our Zeta sinter furnace and need a specific furnace. So I'm going to detail a little more each steps. So first, the file preparation and the printing. As I said earlier, it's almost the same steps that with regular FFS 3D printing process. The only thing you need to consider and keep in mind is the shrinkage. So our parts are going to get smaller during the sintering process, and you need to make your part a little more bigger than the one that will be printed in during the file preparation steps. So for the debinding, I will explain you a little what is happening for the chemical debinding and the thermal debinding. So as I said earlier, our filaments are made with the ceramic or metal powders and with 2 kinds of binder. The first step is to reach the final density to remove this binder with the debinding process. So the first step for ceramic, the solvent extraction, will remove a part of the backbone and of the soluble binder. And after that, we need a thermal decomposition, whether it be for metal or ceramic filaments, that will remove all the soluble binder and more backbones, sorry. And after that, during the sintering, the shrinkage will happen, the part will be smaller, and all the binder will be removed. But I'm going to explain that better in the next slides. So, the sintering. So our parts have a height density, but your print part has only a 50% or 60% density. And to reach this 99% density at the end, it implies a linear shrinkage around 15 or 20%. So what happened exactly during this sintering process? So there is 3 stages. The first one, when you put the part in the furnace, the initial stage is when you have a green part. It's like the thermal debinding, when the backbones and the binder is removing. After, the furnace go up in temperature and up to 1200 degrees Celsius. And there is some neck formation between powder grains, as you can see in the picture. And the final stage, when you will reach 1400 degrees Celsius, the grains with coarsening and the part will be smaller. So is what is happening during the sintering process. So now we explain and detail all the process. I'm going to detail a little more the application by use cases. I'm going to present you some use cases from laboratory, industries, or final part from luxury. I'm going to begin with ceramic example, and after I will introduce you some metal example. Just I'm going to little more water. So my first example is with the LMPCA laboratory. This laboratory is specialized in the study of ceramic material. So they are studying Zetamix part, and they take this advantage and this opportunity to use Zetamix technology in order to make some laboratory consumable and facilitate the supply chain management. So for example, my favorite here, they are printing some thermogravimetric crucible. So here, that is this crucible. Why they are printing it? Because this part is a really tiny crucible and very expensive, and it's only one use part, because the powder can pollute the crucible during the test. Because of that, they have to have a very precise chain management procedure and process, and it's easier for them to print this part and internalize the production of this part than to ask for a quote and wait for the products. The same with the dilatometers consumable here. So it's almost the same research. Is all the thermogravinometric and dilatometers are studying how powder and part behave during the sintering process. So it's a resistant part. Here, the sample holder is in ceramic, and the contact probes here is in ceramic too, and measure how the part behave during the sintering. Because of the high temperature during the sintering, these laboratory consumables can be broken or damaged during the process and have to be changed really frequently. And it's easier and more affordable for the laboratory to re-internalize the process thanks to Zetamix technology. So here you can see the regular consumable you can find in the market, and the white one are the Zetamix one. So the second use case is more industrial, and I'm going to present you the application of Orbital service. Orbital service is a company specialized in orbital welding machine manufacturing. And to improve their product, they invest in 3D printing to solve issues they was facing. So what most important issue they was facing was the oxidation of the part during the welding. Because they are welding parts that are not plain, but that have a round shape, air can interfere, and there are some oxidation. So when the company is welding, they put some neutral gas to make sure there are no oxidation, but because the shape is not plain, there are some link of this gas and the air can interfere. Here you can see with this picture. So they decide to make this part, the trailing shield, in alumina thanks to Zetamix, and to make it perfectly fitting the tube they were welding. So why they need Zetamix technology? Because they need heat-resistant product, alumina, and they need a material that is electrical resistant. to make sure there are no short circuit or things like that. So thanks to this new part, they can improve the quality of the welding and avoid oxidation. So let's move to the third use case with Rozan. Rozan is a company specialized in the production of belt. And this year, they decide to create a belt only with ceramic and no metal to make sure that client can pass through the airport gate without any trouble. So as you can see, everything is in ceramic. This little round here is in ceramic from Limoges, and this is in black zirconia. So for this buckle, this part here, they do not find any affordable solution to produce it. So they decide to make it in Zetamix black zirconia. Black zirconia is a really interesting material for luxury because it has an aesthetical finish. It can be polished or it can have a matte finish, you can see here. And of course, it's passed through the detective gates. So thanks to Zetamix, they can cut the price and the cost of the belt. With regular process, it will be cost 200 euros. And thanks to Zetamix, it's only 30 euros by belt. So let's come back to more industrial application with SAPCO application. SAPCO is a company, a French company, specialized in electrode for industrial boilers. They are producing these electrodes. So here you can see that is one of these electrodes. The white part is the ceramic part, and they are made with, they have two metal slices here. This company for a few years decided to improve their process and invest in a really brand new machine, in particular in an assembling machine that assembles this ceramic part with these two slices. But to do that, they need a welding pin to make sure that everything fit together, the part here. And the machine manufacturer provides them a plastic welding pin. And because it's welding, this plastic part was burning and melting, triggering machines halts every day. So they decide to make this welding pin in zirconia, that is heat-resistant material, thanks to Zetamix, because it's easy to process. The part was made in only 5 days, and now this part has to be changed only once a month instead of once a week, and reducing the machine halts and save resources. So I'm going to come back to laboratory example with Mine Paritech. So Mine Paritech, the same as LMPCA, is studying materials, ceramic or metal material made by 3D printing, and they need sample holder that can resist to high temperature. So here, this part is a sample holder that fits in a tubular furnace. The 6 holes are made to put some long samples, and they need to make it by 3D printing because in a tubular furnace, you cannot put a lot of samples in the same run because the crucible are like just plate and doesn't work, or the sample will touch each other. And thanks to this shape and design, they can put 6 samples in the same run. Another example is with this machine. The mean Paritech needs to heating up a little sample, and they have no machine device to do that. So they decide to use their biaxial machine testing to do that without the option of breaking the part, only with the option of heating it up the part. So to do that, they need some adjustment, and they need to print a new sample order, the white part you can see here, to make it here, to put it here. So you can see the picture. So this part needs to be resistant to electrical induction system, and need to be heat resistant. So you can see here, induction system here, the sample studied, and the alumina sample holder. So I'm going to come back to some more industrial application with Petit Spare part. Petit Spare part is a provider of spare part for the textile industry, and it's important for them to have some stocks or to make sure that they can provide part in a record time. But one day, Petit Spare part has a new kind of order. The clients wanted a part, a thread guide that doesn't exist anymore because the looms they was using was too old. So this kind of part has to be in Zetamix, in ZIRCONIA, because it has to be wear resistant and smooth to make sure that it will not damage the textile. And unfortunately, thanks to Zetamix 3D printing, Petit Spare part succeed to make this part in a record time in Zetamix ZIRCONIA, because part can be made on only 5 days. And after the polishing, the part was really smooth and, of course, wear resistant. So let's focus on more metal application. So I'm going to begin with stainless steel with this Joe. So the industrial want to stay anonymous, but this company wanted Joe adapted to the machine and the part, and wanted on-demand part. So Zetamix technology was a good solution because the part in stainless steel has a very good mechanical strength, and it's possible to make complex parts. The solution enables the company to save resources, because if they would like to do this part with regular process, it would cost 150 euros, and thanks to Zetamix, it's only 30 euros. Another example with A13, the same, the industrial want to stay anonymous. Here, the client would like a custom-made part that can resist to shock and vibrations, and we can post a machine if needed. So A13 is hot and cold tooling metal, so it's the best metal for post-processing. It has a really high mechanical strength, and it enables the company to save money, because with regular process, the same, it would cost 200 euros, and with Zetamix, it's only 30 euros. So I'm going to come back to some ceramic application, two last application with the LEAT laboratory. It's a little different with the last one. So LEAT laboratory is specialized in the researches in new telecom antennas. So they need dielectric material, and they need to test intricate structure. These kind of antennas are in alumina because it's a dielectric material. LEAT is not specialized in ceramics. They just want to research and and find new structure to make new intricate structure in antennas. So that is interesting because it will be a final object that can be used in everyday life, even if you will not see it because it's in the antenna. But here, the laboratory is not focused on ceramic, but on innovation, and they want to answer the question how to improve the antenna shape thanks to 3D printing. And last example with ESRF, the synchrotron of Grenoble. The same as laboratory studied the materials, and scientists who use the synchrotron has only few days to make their researches, and the team that helps them to find the right sample orders and helps them to make the researches has to be really reactive and work with urgent requirements. So thanks to Zetamix, they succeed to improve the quality of sample order and improve the quality of the experiments. So with this example, we can see the heating cartridge done in alumina. Before, it was done thanks to slurries, you can see here. And this heating cartridge was not very secure because there was no wall that separates the two electronical entries. Thanks to Zetamix, they made a part that perfect fit the heating part here with a little wall here to make sure there is no short circuit. So it's easier to make and it's more secure. So we finish with the example. Have you some question? Oh, okay. So a question about resolution. The resolution of metallic or ceramic printing. I'm not sure to understand the question of what resolution you are thinking about. It is the final resolution of the final part. I'm going to check the answer. So I have a lot of documents to answer this. Sorry, I'm just looking for the good document. So I think the answer is 1 millimeter. So the part after being sintering can have only 1 millimeter of difference between what dimension is needed and the final dimension. So, so what is the max size that can be printed? So it's an interesting question. We can print what you want in the printer. There is no trouble with the printer, but it depends on the furnace you have. So you need to have a big furnace if you want to print a big part. With the tubular furnace we provide is only 10 centimeter parts that can be printed because it's the size of the tube. Moreover, if you print big part, you need to be really aware of the wall and the wall thickness. It is too big, you can have some break inside depending on the parameter of printing. But yes, if you have a good parameter of printing and a really big furnace, you can print quite big part, but with the tubular furnace, it's only 10 centimeter. Oh, so a question about the tolerance after sintering. What is the tolerance after sintering? So I really don't know. I'm not technical and I'm not sure I understand the question, but I'm going to note this question and make sure that an engineer of our team will answer you. So I'm really sorry, but I really don't know. So what is the minimum size of the parts that can be printed? So I have a document for that also, because I'm not sure I remember. All this information are in the guideline. If I remember well, we can print a really small part that I'm going to show you with our design guide. It will be more interesting to you to see. So I'm going to share my screen with you. So here is a design guide where you can find all this kind of information on our website in each filaments pages. So for alumina, the minimum size, but it's the same for any filaments, is 6 millimeters by 6 millimeters by 6 millimeters. So you can see the picture here. So I keep going. If we are giving some printing service, no, in NanoE, we do not giving some printing service, but we have partners that can give this service. So maybe we can make you in contact with these companies if you need a ceramic part made by Zetamix. So how long is the whole sintering process? The whole sintering process is around 3 days from the moment you put the part in the furnace and the moment you take it back. At NanoE, for example, we put the part at the end of the week, and all the weekend the part is sintering, and on Monday we have our final part. So yeah, a question about the gas that can be made, that can be used for sintering. It is possible to use mixed gas such as RH5, sorry, I don't know how to say that, for sintering or metallic parts such as stainless steel. So for stainless steel, it's not possible to use other gas. Is really hydrogen that is the best. So I think the answer is no. The best is to follow the guidelines and follow the sintering under hydrogen. And if it's not possible for you, you can print H13, where you can sinter the part thanks to another neutral gas, argon. So I say yes. You said the inox is not sinterable on the standard furnace. Why? Temperature in the standard furnace can work with ceramic. Okay, so yeah, as I just said earlier, inox cannot be sintered in the Zeta sinter furnace, and is not the temperature, is the gas. It do not work with argon gas because the part oxidize. So we really need hydrogen. Is why we cannot sinter it with our regular furnace, because it's not suitable for hydrogen. But our standard furnace, yes, work with ceramic. You can print your Zetamix, ZIRCONIA, and alumina part and sinter it with the Zeta sinter furnace, of course, or other chamber furnace if you have one, other ceramic furnace, of course. So do you have tool to predict shrinkage anisotropy during entering, if any? So we have no tool or specific algorithm for that, but we know what's the shrinkage age in X YAM and Z, I don't know how to pronounce it, sorry. So we know quite precisely what the shrinkage will be. And after we can make such iteration to make sure that the shrinkage and the dimension needed are reached, sorry. Oh, hello, I would like to know how to remove supports printed in Zetamix. It's recommended to do it by chemical attack or by mechanical attack. So depending of how you put the support is a whole subject. You can, for example, put support and remove it after the debinding process if I don't say wrong things. Or you can put the support, depending on what kind of support we are talking about, and put some powder inside between the part and the support to make sure that after the sintering process, you can remove them. I think the best is I will keep this question in mind and answer the engineer that will be able to answer better than me because there are a lot of kind of support and I'm not sure we are talking about the same thing. Yeah, it is possible to use a vacuum furnace for sintering. Yes. For the ceramic, you do not need to vacuum your furnace because ceramic will not oxidizing because it's already oxidized material. So you can use any furnace you want. And for H13, you need to vacuum your furnace to put the right atmosphere inside. But yes, you can vacuum your furnace, but it's important and you have to vacuum your furnace before to sinter your H13 part. And after you need to put some neutral gas such as argon. I'm not sure I answered the question. So there is no more question. I really hope I answer. Oh, there is. So, sorry, I didn't see the question and answer section. So I haven't finished yet. So, so there is some questions that are on both sections. Oh, it's the same, sorry. Yeah, can you send the presentation? Yes, I'm going to send it by email. And moreover, you can find it on our YouTube channel in the webinar recording section. And there are a lot of resourcing about technical things, and you will be happy to find other webinar recording more technical about, for example, design guide for who is interesting, or things like that. Last question, price range per kilo for the filament. So in our website, you can see the price of our filaments. We do not send filaments per kilo because it's a lot, and to make sure that the filament will not be damaged because you don't know, it's hard to use 1 kilo filaments in a small time. We prefer to send it by half a kilo. So in our website, you can see the prices of 500 grams and 1 kilo. So another question, do you make filaments from ZTA composition? So no, we do not make filament from ZTA composition, only from alumina and zirconia. So I'm checking if I answer all the questions. Oh, so yes, one question I haven't seen. What kind of solvent does one need for the first debinding step? So yes, for ceramic, as I said, you need to remove the solvent with a chemical debinding, and we need to remove it with acetone. I checking if I answered everybody. So another question, so in French, I'm going to read it in French. Sorry for English speaker. Serait-il judicieux de mêler cette technique avec une pièce de fabrication additive pour ne faire qu'une seule étape? I'm not sure I understand the question, but it's not possible to have only one step. Because the filaments are made with binder and powder, you need to have the binder removal and the sintering step. It's the same with other shaping process such as injection molding or things like that. So there is no alternative. Feel free to ask me more questions. So I'm waiting 2 more minutes if you have more questions. So yeah, do you mean that the binding stage is chemical and not thermal? Yes, interesting question. The debinding stage is both chemical and thermal for ceramic. So you have your green part, a mix with binder and powder. And the first stage of post-process is remove a part of the binder with the chemical debinding for ceramic. And after, when you put this part in the furnace, you have a thermal treatment in 2 steps, the thermal debinding and the sintering. For metal is different. You have only a thermal post-process, and this thermal post-process is also 2 steps, thermal debinding and sintering. So you need to have 2 steps for ceramic. So what type of extruder is recommended to use for printing? You need to have a direct drive system and not a burden, because it can make some stress on the filaments. They are a little more brittle than the regular polymers one because of the powders. And after, if, for example, you need a special nozzle, no, you can use your nozzle, a regular nozzle, is not abrasive and is not will damage your printer. So thank you for the webinar from one of the attendees. Thank you. So another question, it's not a question, it's comments. For the supports, the ideal is to print the support in the same material, to have the same shrinkage if you sinter the whole thing. Otherwise, you can print your support with any material and remove them after the printing, before post-pressing. If you need your support for sintering, you can remove them with mechanical attack afterward. Yes, I think, yes, it's the answer. It's from Frédéric Rousset, who is one of our engineers. So it's the right answer. Thank you, Frédéric. How does the printing parameters and the printability compare to classical polymer filaments such as PLA and PET? Yeah, so I'm not sure I will answer all the questions, but of course we have some printing parameters. for example, we have to heat a little more the nozzle to 180 degrees for ceramic filaments. And yes, that is the most important to know is the temperature of the nozzle. That can be different. So any other question? Yeah, so Frédéric Rousset, our engineer, is answering your question. The speed of the print is quite lower too for our filaments. Thank you, Fred. So the size of nozzle is depend of the quality you need and if you want to print small part or not. So for the nozzle size, it's between 0.4 millimeters to 1 millimeters. And you can adjust the printing speed, the wider the nozzle, the slower. And 6.6 millimeter is recommended. So it's around 0.4 millimeter to 1 millimeter, and the best is 0.6. So have you other question? I'm waiting just 2 more minutes. So thank you for the comments. I hope you learn things and you enjoy the webinar. As I said earlier, you will find next week the recording of this webinar in our YouTube channel. I will send you the slides, and on our website and on our YouTube channel, you can find other instruction, tutorial video, design guide, and things like that to help you to begin to print and to post-process your parts. So thanks to everybody to join us this morning. And I hope I will see you soon in other webinar or on our YouTube channel, Zetamix YouTube channel. Thank you and have a good day.